Hi, everybody, and welcome to the Virtual Foundries webinar, Basics of FFF Metal 3D Printing with Filamet. We're so happy that you joined us today. It's Thursday, January 18th, 2024. It's about 11:05 a.m., and the temperature today in southern Wisconsin is 5 degrees Celsius. That is it's 5 degrees Fahrenheit. That is minus 15 degrees Celsius for you Celsius users. It is a chilly day, but it's actually warmer than it has been. And we've been experiencing below 0 Fahrenheit temps for a few days. So it's nice to see us above 0. We're looking forward to this weekend when it's 38 degrees Fahrenheit. That's about 2 or 3 degrees Celsius. That will feel like summertime for us, but that's winter in southern Wisconsin. Today, we're going to be talking through FFF metal 3D printing with filament. So this is what we're going to be looking at. What is it? What equipment and supplies do you need? How about designing for the process? Printing overview with tips, tricks, and troubleshooting. Debinding and sintering, that heat process with tips, tricks, and troubleshooting. How does the Virtual Foundries FFF metal 3D printing process compare to other metal additive manufacturing processes? What are the ideal applications for FFF metal? And we're also going to give you some help to get started. Your hosts today are myself, Tricia Cease. I'm the president of the Virtual Foundry, and I handle everything business around here. Also joining us today will be Brad Woods, founder, inventor, and all-around science guy. And who you may hear but not see today is Austin Triggs. He's our print tech. He has the most experience with 3D printing these materials. When you write into the Virtual Foundry, you most likely get a response from Austin. So he's really helpful around here with helping you be successful. The webinar is being recorded and it will be posted to the Virtual Foundry's YouTube channel after today. So you will have permanent access to all the information in this webinar. As we go through, go ahead and type your questions in the chat box. Sometimes we can answer those immediately as we're going through. Otherwise, we will collect those. Austin will throw them onto a slide later in the presentation, and we'll answer them one by one as we go through. So, FFF metal basics. So FFF stands for Fused Filament Fabrication. There are lots of other terms for this style of 3D printing. FDM, which is Fused Deposition Modeling, BMD, Bound Metal Deposition, and lots of other fun acronyms that people come up with as we go along here. And the technology continues. But FFF metal and lots of other metal additive manufacturing techniques follow this same 3-step process: print, debind, and sinter. In the printing phase, you are simply getting material into a shape. And in this case, you're using a regular FFF, FDM style 3D printer to get that shape. Filamet with the Virtual Foundry is made of powdered metal or glass or ceramic. We do have other versions as well, encased in a PLA binder. Now, there are some other proprietary ingredients included there, so we keep that part of it secret, but it's basically metal powder with a PLA binder. So that's why these materials can print just like PLA in a standard 3D printer. And this video shows our bronze filament being printed on a Creality Ender 3 3D printer. So that's the Creality Ender 3 is a pretty basic model of 3D printer. We've used lots of Creality printers around here and really like the brand. And we'll talk through a couple of other brands that work well in just a minute. So you can see that's a really basic overview of the printing process there. Now, if you want, at that point, you can stop and polish your print to a beautiful metal shine. But if you want your part to be full metal, you're going to go through a heat process next. So step 2 is debind. That's where you are getting the plastic out of your 3D print. And you'll do that with heat in a standard kiln. So in that process, you're going to, well, we'll talk through the process in a minute, but that's what the debind step does. And then step 3 is sintering. So you've got all of the plastic out of your part. Now you're going to fuse those metal particles together at the edges in a process called sintering. Now, the equipment and supplies that you're going to need to do this 3-step process are a 3D printer. Well, what kind of 3D printer should you use? We get that question quite a bit. It's an excellent question. Most any standard FFF or FDM style 3D printer will print filament. And we say most any, there are a couple of exceptions. There are a few brands of 3D printers that lock down your material selection. So you can only use their branded material. Obviously, ours won't work in that group. We have also seen a 3D printer here and there that makes it very challenging for the filament to get through its system and onto your build plate. But those are few and far between. If we're talking about the major brands, Creality, Bamboo Lab, Ultimaker, Prusa, Raise 3D, and a bunch of others, those all work really well with these materials. If you want to get a little bit more information, take a look at the podcast that's listed there, and Austin will drop a link into the chat where we do more of a deep dive on what printers work with filament. Direct drive, dual gear direct drive is typically going to be better than Bowden tube. And you're going to need a 0.6 millimeter hardened steel nozzle. So being able to change your nozzle is important as well. Continuing down the list of equipment is a Filawarmer. That's that device that you see connected to the spool, and then this larger picture of it here. That Filawarmer warms the single strand of spool as it comes off, single strand of filament as it comes off the spool, makes it a little tougher, a little more flexible, and just eases the path from spool to printer for the material. Blue tape is on the list because filament can really stick to your build plate. So having some, in this case, it's kind of a release layer to help the filament from sticking to your build plate very hard. In the case of a glass build plate, you would use a glue stick, or no, we have updated it. Austin, tell us a little bit about preparing a glass build plate for filament.
So when you're using a glass build plate, you'll actually want to use isopropyl alcohol, typically somewhere around 91%, to wipe down the build plate so it's perfectly clean. And sometimes before you use the alcohol, you can go over it with a little bit of dish soap if you have some issues. And once it's spotless, you'll want to heat that up to 65 degrees Celsius for the entirety of the print.
There is a video about that on our YouTube channel as well. So Austin talked about isopropyl alcohol that applies to glass build plates. So otherwise, blue painter's tape really does the trick nicely. And then of course you need some filament. Now for the debind and sinter process, the equipment and supplies that you'll need are a kiln, first of all. Now you can use a regular desktop kiln. The 2 requirements for the kiln are that it has a programmable controller and that it can work and hold the temperature of the sintering, or that it can hold the sintering temperature of the material you are working with for several hours. Well, how do you know what that is? On our website, you will find a list of our materials and the sintering temperatures that you will need to achieve. So your kiln will need to hold those temps for several hours. So as long as it has a max temp of a little bit above that, you'll be fine. We're talking about, our process is suited for open atmosphere. That means you don't have to use any gas or vacuum. Now you can. Oxygen needs to be prevented from reaching your part during sintering, whether you accomplish that with the method that we use, which we'll talk about in a minute, or gas or vacuum if you're used to that. But an open atmosphere standard kiln, like a pottery kiln, is great. You'll need a crucible. And the crucible is that little white cup that you see in the center there. That crucible is going to hold your part and its support material during the debind and sinter process. You'll need refractory ballast. I just said sintering material, and that's what I mean by that. We're going to use Al2O3 or aluminum oxide and magnesium silicate when we're working with copper and bronze. We're going to use steel blend when we're working with the steels. You'll need sintering carbon, and that is the item that manages oxygen and keeps it from damaging your print during the sintering process. And then a crucible cover like kiln paper or a ceramic plate. And we'll talk more about the purpose for that in a minute. Now, looking at design for additive manufacturing, and here's where I'm going to ask Brad to chime in a little bit, but there are some part shape properties that work best in this process. We've certainly got a sweet spot for that. And I'll tell you after Brad talks through those, I'll give you some tips on going outside of those parameters.
Sure. Am I on?
Yeah, go ahead, Brad.
Okay. Pieces that thick tend to be more challenging. So if you picture during the debinding process, the plastic that was holding the metal particles together needs to leave the object. And when you have a thick, blocky part, it can cause distortions as it's leaving, and it can cause the surface of the part, we call it pillowing, where it will delaminate slightly and it'll get sort of a pillowing look to it. This can be overcome, but the easiest parts to do are parts that are, say, 3 to 5 millimeters thick at the maximum, and this makes it very simple for the binder to leave the part during the debinding process.
So Brad's talking about thickness. Now you see a couple of parts on the screen there, and I do have those in my hand. So if you can see me a little bit, here is that Easter Island head. It's massive. It's about 6 pounds of copper. It's about the same size as my head. This one is sintered, but it did suffer a little bit from exactly what Brad is talking about. It had a little bit of a blowout as the gas was escaping during debinding. Now that Coliseum print is turned out beautifully. So it's a large print, but it has smaller or thinner uniform walls. And so that one turned out great. So you can see the difference between those two. Thinner walls are going to work best. Holes and threads, you're going to tap those after the fact. So you might, in your model, make those a little bit smaller and then drill them out later. And infill, we're going to talk about recommended infill percentage in a minute, but we do also have tips for going outside of these sweet spot parameters. And one of those is in the What's the Biggest Part I Can Make podcast discussion. So Austin will put a link to that one in the chat here. If you want to know how to get to the size of the parts that you're seeing on the screen and how to go outside of what's best for the design parameters, take a look at that podcast. There'll be a lot more information in there. Okay. Now we're going to talk about printing overview. So the basic print settings are nozzle is, like I said earlier, it's going to be very similar to regular PLA. Nozzle temperature of 210 C, a flow rate of 135% or extrusion multiplier 1.35, depending on how your slicer names that setting. The sweet spot for infill is 70% infill with 3 wall lines. Now, if you want to go outside of that, well, I want my part to be 100% thick, or I want my part to be 100% hollow. We have tips for going outside of that 70% infill as well in a podcast about how much infill should I use. So Austin will throw a link to that in the chat as well. Now, what support material should you be using when printing with Filamet? You will use any support material that you would use with standard PLA, including PLA itself. So all of that support material will be broken off. Using the PVA water soluble support is a great option as well, because then you can just soak all of that off before you go into the heat process. Now I'm going to hand it over to Brad again to talk about making adjustments as you begin the printing process. He'll talk about those two photos that you see here. And Brad, talk to us about clogs as well in your discussion.
Sure. So in the photos, this is a bronze piece, the photo that's on the left. The one on the left of that is under extruded. So there just wasn't enough material coming through the print nozzle to fill in all of the area that was meant to be covered by the 3D print. The one on the right is about perfect. This is about where you want it. These lines are, the print lines are quite visible in this one, and depending on your printer, that will vary, but that's what it should look like. The one to the right of that is an over extrusion. So this is one where the infill was 100%, or at least the top few layers were at 100%. And more material was being put on the print than there was space available. So the nozzle winds up pushing the material to the edges of it and will build up like little attachments to the outside of the 3D print. Let's talk about, okay, so the infill, 70% infill, the reason this works well is that it isn't solid. And at 70%, 30% of it is open space. So that provides channels for the gases to escape during the debinding process. And there are always exceptions. It can be printed at 100%. There's ways to do it. It can be printed at nearly hollow. There's ways to do that also. It just takes a little bit of understanding.
So let's talk about clogs as well. Sometimes, yes, your nozzle does just get clogged up with filament, but a lot of times what looks like a clog isn't really a clog. Excuse me. And one example of that is that the material needs just a bit more room between the nozzle and the print bed on the first layer to squeeze out this thicker material than PLA. So Brad, talk to us about some common things that can look like clogs and ways to correct those.
Yeah, the number one most common is what you were described, where you need a slightly greater Z offset to keep the nozzle away from the build plate so that there's room for the material to extrude. Our composite materials are very viscous compared to regular PLA. They have a consistency more like bread dough than a liquid plastic. What was next?
We were just talking about clogs. Is there another way, or when you do have an actual clog, how do you clear that out?
Okay, right. And the second most common thing that looks like a clog, but it's not. Well, technically, it isn't when it started, but it becomes one. So our materials have lots of metal in it, so they conduct heat really, really well. So you'll have a situation called a heat creep, where heat that was at the nozzle will climb back up through the filament to the point where it gets to the drive gears and it becomes soft. And this will initially present as a clog, but it's not. The material could still flow. The nozzle isn't mechanically clogged. But then what happens is it sits there and then it does become clogged. The general remedy for fixing a clog is just like PLA. You can take the nozzle off and run it out with a drill bit, or most people that do a lot of 3D printing have their own favorite technique for correcting a clog. And what you use with PLA is what you will use with Filamet.
Now, one of you had asked about filament storage in your registration form, and also thank you for filling out what you wanted to learn in the podcast today. That really helps us tailor it to you. I'm sorry, the webinar today. Filament storage, you don't need to worry about any special conditions for storing your filament as long as it's in a standard climate control indoor environment. You want to keep it away from direct sunlight. You want to keep it away from direct heat sources, storing it right in front of a register, for example. But in standard indoor climate controlled environment, your filament can be stored open. If you are in a very humid environment, you may need to work on finding a drier place for it. Do not dry your entire filament spool at once. Do not put your spool in a filament dryer. It will render the entire thing brittle and unusable. It's important to only use that filler warmer for heating your spool. Don't heat your whole spool at once.
Quick question,
Daniel,
guys. Yeah, I got to run, so sorry about this, but I was really curious before I go. What's the loading ratio with that copper? Is it like 70% resin and, or sorry, 30% resin and 70% copper? What's the loading ratio on that?
Yeah, all of our materials have a different material loading. Copper is something around 90% copper, 10% plastic. But all of those percentages you can find on the products page of our website.
Great. And then the other one, have you tried for those thick pieces? Have you tried to soak them in acetone for a couple days and then debind it after, or get the binder out that way?
Right. So you're describing a solvent debind, and we have not found a good way to do this.
Okay, gotcha. Well, I do that with Tethion's Genesis resin, but it probably is different with your guys' process. But thank you for enlightening on that. I appreciate it.
It's pretty resistant to solvents. The best solvent we've come up with so far is dichloromethane. That will at least break down the polymers a bit, and tetrahydrofuran also can work. But we haven't done a lot of development in that direction.
Thanks, I appreciate the.
So gang, these basic print settings are all on the website. You don't have to rely on what you're learning in the webinar today for all of the information. The Learn tab on the website is where you'll go. I'll mention this several times, but all of the print settings are listed there. If you have a Bamboo Lab or Ultimaker printer, we have a couple of additional resources for you on our YouTube channel. Just search for Bamboo or Ultimaker, and you'll find some additional printing tips and tricks for those two printers. The Bamboo Lab actually makes it a little easier, fewer things to adjust. And then we have some tips for setting up your filler warmer with the Ultimaker on the YouTube channel as well. Let's talk through that debinding and sintering process. I know a lot of you are most interested in this part. 3D printing is 3D printing, right? So debinding and sintering, the basic process is this. You've got your crucible, which in that photo you can see is the little cup inside the kiln. You'll put your Al2O3 or steel blend powder in the crucible cup. You'll bury your print in that, pack it down, and put your crucible in the kiln. Run the debind cycle. The time and temperature profile for that is all on the website in that Learn tab as well. That process is going to take about a day. It's pretty long. So maybe 12 hours from room temperature to room temperature. So you set it and let it run overnight. Come back the next day, you'll take your crucible out. In the case of bronze and copper, you're going to empty the contents of the crucible and then go through that same packing process again, but this time with magnesium silicate. Bury your bronze or copper part in that magnesium silicate. And now you're going to cover that magnesium silicate with a layer of sintering carbon. The sintering carbon is very important. It's what prevents your part from being oxidized during the sintering process. So you can't use too much sintering carbon. It's meant to be consumed as the oxygen, as it reacts with the oxygen. You can minimize the amount of oxygen the sintering carbon has to manage by covering your crucible then with a piece of kiln paper, which is what you see in that photo. That crucible has a little piece of kiln paper on it, or a ceramic plate or something like that, as long as you're not creating a tight seal. Now, in the case of steel, we've buried our print in steel blend and run the debind cycle. And then we're going to take that out the next day and add sintering carbon to the top. Back into the kiln it goes, into the same kiln, and run the sintering cycle, time and temperature profile. Again, all of that is listed on our website on the Learn tab. Glass and ceramic, the difference with those two materials is that they love oxygen. So there's no worry about oxygen during the sintering process. So you will skip the sintering carbon altogether. Now, one question that we get quite a bit is, can those sintering powders be reused? And the answer is yes, absolutely. We've got some information for you on that. Austin is going to put a link to a blog post that talks about the sintering powders, reusing them, when to know when you should replenish those and get fresh powder. Now, some things that can happen during the debinding and sintering process, or the most common things that can go awry, are pillowing or doming. This is something that Brad mentioned earlier. That's when the gas that's coming out of the part kind of pushes out on the part and creates a dome or causes some delamination between those outer layers. So step number one that we're going to tell you is to really pack your part for the debind cycle. You can think about even ramming in that they do in other industries. Just get it nice and tight. Even apply a weight to the top of your crucible for that debind process. And the idea is that you want to compress your part in that ballast. One of the more common errors that we see in sintering is that the part comes out completely black. Well, black means it's been oxidized. If your part comes out black and crumbly, it was oxidized. So question number one that we're going to ask is how much sintering carbon was left at the end? Is there any new looking fully black sintering carbon left over? That's going to be your key. And if there was not, then absolutely your part was oxidized. And the cure for that is more sintering carbon, but then also applying that cover to help limit the amount of oxygen that the sintering carbon needs to manage again. So that's going to be the key there. Now, what if your part comes out at the end of the sintering cycle and it's kind of a glob? It's lost all of its corners. It is unrecognizable. Well, your part has been over sintered and actually melted a little bit. So the good news is you've got some good metal there, right? But that's not really what you wanted. You wanted your part, well, you do want good metal, but you also want your shape to be true. So in that case, we're going to pull back on the time or the temperature. And Brad, talk to us about how the time and temperature work together.
Right. So in sintering, and this can be a little confusing because there aren't hard numbers on the time or the temperature. A good sinter is a combination of those two factors. So you can get your part to sinter more by either extending the time or increasing the temperature. Getting the right balance. If you follow the directions on our website, you will get a success early on.
And everyone's equipment is different.
Yeah, and this can be part of the challenge. And this is also true of the oxygen issue that you mentioned earlier. Some kilns are more airtight than others. And you'd be surprised at the amount of temperature variation in the temperature controllers on the kilns. They can vary plus or minus, 20 or 30 F. Pretty commonly, we see this come up a lot. So, so it can be a matter of a little bit of tweaking. Take a look at the piece, and you can send us pictures, and we've done thousands of these. And at a glance, we can tell you what you need to change.
So we're talking about some of the more common issues that happen, but we also don't mean to scare you. The process is really straightforward, and it's actually very much like cooking, right?
Yes.
You've got some equipment that you need, you've got some supplies that you need, your ingredients, and there's a specified process that you follow, and including time and temperature. So very much like cooking, as long as if you follow the instructions, you'll have a high chance of success. So we strongly encourage people just to follow the instructions that we have on the website as written. Once you get that process down, then experiment as you choose. One of the benefits of this process is that you have complete control and flexibility over every aspect of the process. So once you understand it, then yes, by all means, tweak it, work with it, try new things with it. For your first time out, just follow the recipe.
Yeah, I'd like to reiterate this topic. The number one troubleshooting solution we provide is reminding people to follow the instructions more closely. It seems like you should be able to just improvise a little bit, like you're throwing some extra seasoning in it or something like that. but just get a victory, get a good part, and then start to change the process.
Now, lots of people asked about aluminum in the registration forms. Aluminum and titanium are different. They are reactive in the presence of oxygen and heat, which is no bueno. So you're not going to be able to sinter those in standard kiln equipment like we've been talking about. They both require specialized kiln environments in order to do that processing correctly. And we're going to add a little bit of a note about tungsten as well. Our Rapid 3D Shield tungsten filament is a really awesome special product. It's designed to be a non-toxic 3D printable replacement for lead in radiation shielding applications. And the beauty of this material is that it provides that benefit in its green state, meaning as printed. So you don't need to go through that heat process to get the benefit of X-ray shielding that you can 3D print on your FFF 3D printer. So that one's really special. We do have a podcast that gives more information about aluminum and titanium and how they're different. Austin will throw a link to that one in the chat as well. Now, there is some really fun debinding and sintering technology in the works. And one of those that's most exciting to me personally is using a standard household microwave. The general process is the same. You're going to use a ballast material. You're going to bury your print in that ballast material. You're going to run a prescribed time and temperature profile. You're just using a microwave instead of a kiln. What you do need is a special container, and you can see the photo in the center of the screen there of that special container. It's lined with metal. So that's what makes it special. It's called a microwave kiln. If you go to Amazon and Google microwave kiln, you'll find a bunch of options there. You can see it has a hole in it. That hole will need to be plugged to prevent oxygen from reaching your part. But it's a pretty basic piece of equipment. We have some information on our website in the blog section about microwave sintering and calibrating your microwave for the process. And you can also take a look at Mr. Highball's YouTube channel. He has done the most work on this process and is beginning to release a step-by-step tutorial on it. So he started with aluminum and titanium, which we just talked about being a little more involved with the debinding and sintering process. He wanted to go with the most challenging materials first, and he has had some successful parts come out of that. So take a look at that if you're interested in that very exciting topic. Now, the sintering chart, this is on our website, the same chart. You'll find this on the debinding and sintering instructions page, but it's going to talk through the different materials, what crucible type is great, what refractory, what sintering powders you need, the debind temperature, the sub-sinter temperature in the case of steels, which you'll see that in the instructions, and the sinter temperature. So that's all on our website. This gives you a basic overview of the sintering temperatures you need to reach. If you have a kiln that gets to 2350F or say 1280C or cone 10 in pottery speak, you've got it covered. This is a great question about comparing Virtual Foundry to BASF, and it's an excellent lead into the next topic where we do a comparison of the Virtual Foundry with the other FDM metal processes out there, including Desktop Metal, the Mark Forged Metal X, and BASF Ultrafuse. This data is from a webinar that we did in May of 2022, so some of it may be a little dated. But you can see an overview here, and talking more specifically about BASF Ultrafuse. The printing process is going to be very similar. The Ultrafuse likes to have a heated chamber on the printer. The Virtual Foundry's Filamet does not require that. But printing is very similar. Where it gets really different is in the debinding and sintering process. Ultrafuse uses a catalytic debind process and a special sinter process. You need to send your part away to a service bureau to perform those for you. You can't do those in-house. There are some equipment brands looking to create a system that will process the BASF materials from start to finish for you. Again, you're dealing with that chemical debind situation, though, rather than just using heat to debind. So that's the major difference. The printing is fairly similar. The end result is the same. It's that debind and sinter process that's really going to be different. And you can see here some of those differences there. Another difference with the virtual foundry is that you can do the entire process offline. Your part data never needs to be sent to the cloud. So your slicer, your 3D printer that you choose, your kiln that you choose, none of that needs to be connected. So your part data can be 100% secure. You're doing the full process in-house on your own. The next page, this chart as well is on our website. Austin, will you throw a link to that on there? It's on the resources tab. The second page of this comparison chart, again from May 2022, and that's where this date becomes more important, is the costs. So a couple of you asked about costs for the system and getting parts out of this system. We do have a video on our YouTube channel. Awesome, we'll link to that as well. That talks about going all in on a full metal 3D printing system and what your first part cost is. We give all the caveats and the exceptions to what's being said, so you'll get the full information there. But here you can see the Desktop Metal Studio system and the Metal X by Mark Forge are a significant investment. UltraFuse and the Virtual Foundry are more of a similar investment on the filament side of things. The equipment is where it gets a little bit different. You can get you're buying the kiln of your choice to process the Virtual Foundry materials. With BASF UltraFuse, you're sending your part away. UltraFuse does deeply subsidize the cost of the debinding and sintering process. I think you only need to pay something like $50 per kilogram of parts. Your part can be away from you for about 2 weeks, and that if you wanted to buy a system like I talked about that some equipment manufacturers are working on, I'm hearing prices of $100,000 and up, so you're getting into the similar territory as the closed systems offered by Desktop Metal and Markforged. So again, this information is on our website. We also did a webinar in May of 2022 that gives a lot more detail about these different systems. If you're in the shopping phase, I definitely recommend checking that out. Now, ideal applications for this process. Brad, I'm going to hand it over to you here to talk through the ideal applications and some applications to avoid.
Sure. People's first thoughts when they think of metal 3D printing is they think of it as a replacement for CNC and casting and things like that. And we encourage people to think about this a little bit differently. It's a nice complement to those things, but our objective is not necessarily to produce millions of parts using this technology. So it works great for one-offs. Research and innovation is probably our largest buyer. I mean, that's where most of what we send out goes, is to different labs and schools and things like that. Parts to avoid, just things that are big, bulky, take excessive amounts of stress and strain. This is a new way to fabricate metal parts, and historically this doesn't come up very often, so it requires a little bit, think about it a little bit differently. Be open-minded. Don't try to replace or don't necessarily try to replace what you're already doing. Look for new methods of innovating and new solutions. Right behind the pop-up there, hang on a second, there's an image. I'm waiting for Austin's message notification to go. There it is. So this is a technique called generative design, and it comes from generative artificial intelligence. So you can see the progression in that part. The one on the far left was traditionally designed with CAD software. As you move to the right, it's further and further iterations of a generative design process. So rather than making that bracket, for example, you describe the parameters to it. How much strain will be on each of the bolts? Which direction will the strain be coming from? But this is an incredibly cool topic.
Yes, thanks, Brad. Right on. We did do a webinar about ideal applications. I know you're sensing a theme. There's a video for everything, right? But yes, we want to give you as much information as we possibly can to help you be successful. So definitely rely on the YouTube channel and the blog section of the website for additional information about every step of the process. Research and innovation is listed there as #1, and that gets us super jazzed. Students and professors all over the world are doing really cool work with this process. Check out the research and white papers page on the website for a list of published papers that are either about this process itself or that use this process in service of another topic like green energy. And there are lots of papers listed there, more come out all the time. So if you are at an educational institution on the webinar here today, and I know that several of you are in good company. Take a look at that list and see what your colleagues have been doing all over the world. So where to next? How do you even get started? Well, we have a solution for you, and that's the Getting Started bundle. Now, this bundle is going to include everything that you need to do the full process start to finish, except your printer and your kiln. You will need those yourself. We can help you with the kiln if you need one of those. And for attending the webinar today, you can get 7% off of your Getting Started bundle if you use this code IWANTFFF metal. So as you choose the Getting Started bundle in the store and during your checkout process, enter that code, you'll get 7% off your Getting Started bundle. But we're not stopping there. We offer a full FFF metal 3D printing course. Now, this is a super deep dive on every aspect of the topic, going way further into the things that we talked about today and adding more design and part cleaning and post-processing to the end of it. Emerging technologies, we go much farther, much deeper into every aspect in this course. It's 7 sessions over 14 weeks. It starts this spring on February 29th. It's a leap year this year. It starts February 29th. For attending the webinar today, you can get 10% off of your course registration by entering code TVFFan24. And you'll see it's at courses@thevirtualfoundry.com. So take advantage of that offering to really understand the full metal 3D printing process. You can try to gather all the information in the various places that we have it, or you can talk to us directly, get all the information firsthand, work with us. We're going to send you a kit of materials for you to work through the process. It's like personal application development. Now, from there, more resources to help you get started. I've been talking a lot about the YouTube channel, and for good reason. We have a ton of videos on there. Take a look at the playlists. There is a how-to playlist, and this one will generally walk you in order through the process. It answers those other ancillary questions. How do I set up my filler warmer? What about those sintering powders? How much filament am I going to need for my part, etc. And it goes into some other topics as well. So rely on that YouTube channel as a resource. All of our podcasts are there, and there's also just a couple of other fun things on the YouTube channel. The Discord server, this is a cool spot for our partner innovators. That's what we call you, our customers, to come in and talk to each other about what you're up to, ask each other questions. The TVF team is in here as well, talking with you. So lots of good info in the Discord channel. So come here as well. You will find a link to that on our website on the community tab. We talked about the course. The getting started page is a great place to start. You're going to see the basics like we talked through here, the equipment that you need, basic printing settings, and then it's going to link you to pages with more information. And the Learn tabs. This is a great place to start on the website. I've mentioned this several times through the video today. The Learn tab is where you're going to go for all of your instructions. The Getting Started page that we just saw, the printing page, the debinding and sintering page, and also information about finishing your metal parts, which we really didn't cover in the webinar today. But basically, any process, polishing, brazing, welding that you are going to do to regular metal, you're going to do to these final parts as well. You can always write to us, and we encourage you to do so, info@thevirtualfoundry.com. We'd love to celebrate your successes with you. It's so fun to see your parts. All of you are doing wonderful creative things. So please show us what you're up to. We love that. We can certainly put together a consultation and training package specific to you and your needs. And then also another link to that compare and contrast FFF metal is right here in the webinar, so you can find that one. Now I'm going to do this. I ask you to talk amongst yourselves for a second while I get myself ready for the next thing. Okay. Here we go. We just had a couple questions come through during the webinar, and they are specific to iron. So is there a replacement for pure iron in development? Help us with that one, Brad.
We're working on it. Pure iron has been surprisingly challenging to fabricate, and it works the same on the sintering and everything on the back end, but it's been a challenge to come up with a filament format that isn't brittle. But we will solve this problem. In fact, we probably have the solution in in the pipeline right now. We're getting close. We'll roll it out as soon as we can.
Making the filament is always about finding the balance between highest material loading possible and usability. So we can always get more material in the filament, but there's a point at which it becomes unusable and overly brittle. So Brad's always looking to find that balance between the two, and the pure iron was one of those materials that just came out super brittle. Lowering the metal content would help that, but then the material becomes not as useful if you're lowering the metal content.
Yeah,
So
the shrinkage factor becomes incredibly high as you lower the metal content.
more about iron. What is the expected shrinkage of high carbon iron when you're sintering it?
As solid as possible is the key part of that statement. And at 98% density, which is about your theoretical maximum using this process, it will have shrunk by about 20%. So the shrinkage is pretty substantial as you get towards the higher and higher densities.
So let's talk about shrinkage. We didn't cover that in the webinar today. When following the instructions on our website, you can expect 7% shrinkage for copper and bronze, 10% for steels. Now they're going to shrink the same on the X and Y. There may be slightly more on the Z due to gravity, but that's what you're going to expect. At that rate, you'll be at about 85% density in your final part. If you want more than that, you're going to extend your sintering hold time to further densify, which means shrink your part. Have you considered doing a low carbon steel?
Yeah, in fact, I mean, we've done variations of this. We do, we'll make custom versions of filament for different companies all over the place. And we've done versions of things like this. So likely we will bring one of those to our store at some point in the relatively near future.
We do have a new version of steel. This is a teaser for you coming out in a couple of months here. So pay attention to the emails, the social medias, and things like that. And you will get information about the new steel that we're rolling out in the next couple of months here.
Yeah, we've been working on materials with more scientific applications. So things with high magnetic permeability is a good example. We have a lot of applications where we have a lot of users experimenting with green energy solutions. So more efficient motors, different methods of storage. And yeah, so we'll be releasing more materials with very specific scientific applications or properties anyway, as well as some of the just more simple steel.
So folks are asking about specific materials. We can always make that for you.
Yeah.
So we do offer custom materials. If you got a special metal or glass or ceramic that you are interested in and don't see it in a 3D printable form on the market today, we can very likely make that for you. Reach out to us and we'll talk about a custom run for the material that you need. Now, finally, this is our final list of resources here. The Discord server we talked about, all of our socials are listed here, Reddit, lean on that YouTube channel, LinkedIn, Facebook, the instructions on our website, Learn tab, the shop, that's an important one. And we are at info@thevirtualfoundry.com. So Brad, that concludes all of our questions for today. And I know that this would be the time when I would ask you one more very important question, and I'm sad to say that I am not fully prepared for that.
All right.
Awkward pause, and we're going to close the webinar. Thank you, everyone, for joining us today. It was great to talk with you. Thank you for asking those great questions as we went along. Again, this will be posted to the YouTube channel, and I'll email you once that's ready. I Want FFF Metal gets you 7% off your Getting Started bundle. TVF Fan 24 gets you 10% off your metal 3D printing course registration. So take advantage of those opportunities. Thank you for joining us today, and happy printing, everybody.
Thanks, everybody.